Yes. Okay. Welcome everyone to the virtual lab tour at ITRL. So before we start with this breakfast seminar, we have a few instructions. First of all, please make sure you keep your mic muted until you wish to speak. And the same for the camera. Please make sure to keep it turned off until you want to ask a question. There will be different presentations today. If you have any question you would like to ask, you can always write them in the chat. We will have some time between presentation where we can ask some questions. And if you want to speak, make sure to raise your hand and we will hand over to you to ask your questions. For more breakfast seminars, you can check our website on events under ITRL.kth or find us on Facebook and LinkedIn. So for today's agenda, so we will start with some introduction about ITRL and the upcoming open house event we will have after summer. And after that, we will have a series of presentation covering a bit all the labs and project, or like mainly labs that we have here in ITRL. So we will start with Smart Mobility Lab. We will move on with the Space Robotics Lab. Then we will talk about the research concept vehicles. And finally, the remote driving station. After that, we will have some time for discussion. So we will open up for all the questions you might have. And yes, before we move on, I'll briefly introduce our speakers today. My name is Elisa, and I will be the moderator. Then we will have Kaj, that is a research engineer in ITRL, and we'll talk about Smart Mobility Lab. Then Pedro is a PhD candidate at the Division of Decision Control Systems, and he will talk about the Space Lab. And Mikhail, associate professor at ITRL and vehicle engineering, and we'll be talking about the research concept vehicle. And finally, Shiji, which is the research engineer, vehicle engineering, and we'll talk about the remote driving station. Yeah. So before we move on, I would like to welcome ITRL Director Jonas for a brief introduction about ITRL and the open house.
Okay, thank you, Lisa. Okay, and again, very welcome to this seminar. Just a very brief introduction to ITRL, if there is anyone that is new in the audience. ITRL is a research center between KTH, Scania, Ericsson, Region Stockholm, and Trafikverket on sustainable and integrated transport systems. So we have been working together since 2015. And we work on connected and automated vehicles, on electrified transport systems, on vehicle concepts, and on mobility and logistics systems, and in particular how these sort of integrate and connect to each other. And as an integral part of our activities, we have our labs, and this is what we are showing off today in this virtual lab tour. But then we also have a large number of research projects. Some of them are connected to the labs that we show here, some are not, and some are connected to field trials and experimental facilities with our partners. So after the summer, we will host our open house. It's a yearly event where we invite all our collaborators and interested people into ITRL to see what we are doing. We will, of course, again then showcase our labs, but we will also show a lot more about ongoing projects, and our partners will be present to show how they collaborate with us in ITRL. So very welcome today to this lab tour, and also very welcome to come back after the summer break to join us again for the open house. Okay, thank you.
Thank you for the introduction. Yes, then we move on, hopefully. Yes, here we go. Yes, so I would like to invite our first speaker, Kaj, to join us here and talk about Smart Mobility Lab.
Thank you, Lisa, for the kind introduction, and thank you everyone for joining this presentation on Smart Mobility Lab, or what we usually say SML. I want to start with going to the next slide, like this. No, I want to start off with maybe the most common question I get when talking about my work on connected and automated vehicles, and that is, where are they? They were supposed to be here years ago. So what happened? And for me, that's a bit difficult to answer. I don't have a complete answer to that question. Some would say that they are already deployed. Others are afraid of a long tail development. But what I usually do is flip the question, like, what technology are we talking about? What is autonomous vehicles for you? Because I find that when someone says autonomous vehicle, they already have their own expectation on what that is, what the problem is trying to, what the autonomy is trying to address. And that can be vehicle-to-vehicle interactions, human-to-vehicle interactions, logistics, communications, and so on. So in our lab, we look at all these different problems, and we recognize that, well, it's kind of the same thing that the same research questions that we look at in robotics. While I work specifically on self-driving technology in SML, we keep a lot broader view on mobility, whether it's autonomous vehicles, a robotic arm, or drones. They all share the same higher level problems. So Smart Mobility Lab is somewhere where transport meets robotics in some sense. And by engineering real systems, as you see in the image here, we try to carry over what we learn about mobility from one domain to another. So for instance, some of the challenges that we are looking into is, how do we ensure safety while still achieving the set out goals? How do we deal with unpredictable environments? What happens now when we have unprecedented connectivity with, for instance, 5G? But none of these challenges are necessarily belonging to one domain. So as I said, in Smart Mobility Lab, we try to look from one system to another and see what can we carry over. Now, I believe that working on a real system is fundamental into bringing research into the real world, which is why I really like everything that is presented here today. And in SML, of course, we have a few of these research platforms. And I will start off with the one I work with mainly. So this is SVEA. It stands for Small Vehicle for Autonomy. It's an RC car, 1/10 the scale of a normal full-size car. But we've equipped it with all the sensors and gadgets that you would typically find in an autonomous vehicle. And with it, we can put any sort of self-driving technology on it and test the performance of it in a controlled environment. For instance, we can use SVEA to develop control towers and remote operations setups, like in the image here. And on the topic of remote operation, we have, as Elisa said, a later part about that as well. But not only autonomous vehicles, as I said, we also look at more traditional robotics. So we have a few platforms in lab where with these kinds of omnidirectional robots that can move in any direction. We can, for instance, use them to solve coordination problems, like if we have many robots, they need to form some sort of they need to stay in some formation in relation to each other. We also look at different sorts of collaborative tasks. Here we have 2 drones, which we've worked a lot of on in the past. And the 2 drones are picking up an object. And similarly, we also have done work with robotic arms that need to cooperate in picking up heavy objects. Now, I can't speak for all of these platforms. We have many PhD students, research engineers, master thesis students that come into the lab and work on different projects, essentially. But in my work, I'm trying to develop something I call for regional intelligence. So this is an edge cloud service that provides support for connected and autonomous vehicles to help them make better decisions. That could be providing unified information from connected infrastructure to tell the vehicle, hey, there's a pedestrian around the corner, or to coordinate all the vehicles in this region to optimize traffic flow. And you can see the regional intelligence as the automation of the local area itself. And the area could be a few intersections, as in the leftmost image, or maybe we have a contained region like a logistics hub. And we try to support the vehicles in some way to help them make better decisions. But I shouldn't stay too long on this topic, otherwise I might take over the entire seminar. So I want to show a few snippets of the experiments we run in lab. This is an object detector that looks at the differences between each frame to identify where the vehicle is. This is highly efficient, this algorithm, and could be very suitable for infrastructure sensors. The next one is just about these collaborative tasks that I was talking about earlier. Here we have a ground robot cooperating with a drone, picking up some object and moving it. And finally, if we have time, I want to show a video trailer of Smart Mobility Lab. I hope this will work in And with that, I want to say thank you. And back to Lisa.
Yes.
Oh, yes, of course, of course.
Yes, thank you so much for your presentation. If there are any questions from the audience, please write them in the chat or raise your hand here. Otherwise, I will start. Yeah, I was wondering if you can tell us something about the hardware equipment that you use for your experiments.
The
hardware that you use
yeah.
for experiments.
So as I said before, I might not be able to talk about all the platforms, but in my work, I use the SVIA platform, and as I said, we have all of these sensors and gadgets equipped to it. That include LiDARs, stereo vision odometry. We also have IMU sensors. We're currently equipping RTK GPS as well to localize outdoors. But none of these would work without a fairly powerful computer on board. So we have these NVIDIA Jetson computers that allow us to utilize a dedicated GPU for running object detection, etc.
Thank you so much.
Yeah, I saw in the video of this object detection that, I mean, it looks like it works quite fine, but
yes.
it lags a little bit behind, and there was at some moment you could see a misdetection as well. So can you say something about how you can handle those situations?
Yes. So this particular algorithm is not suitable for detecting that this is a person, this is a Svea, because it's kind of simple in design. It only looks at what has happened in between each frame, and then it tries to, well, contain that region of difference. So we're not thinking about using this algorithm to robustly say here is an object. But we're thinking that this algorithm might be very useful in tracking objects over multiple frames. So you might have a traditional deep neural network to detect this is a pedestrian, this is a bicycle, and then using this algorithm, we might take the same region and look at how it moves throughout time, and that can be particularly useful because, as I said, this is highly efficient, while deep neural networks might perform much slower.
Thank you, Kaj.
Thank you.
Great. Now we will move on to the next speaker. So I would like to invite Pedro here to talk a little bit about Space Robotics Lab.
Hello. Thank you, Elisa, for the introduction, and hi, everyone. So I will continue where Kaj left the presentation. I'll be introducing what we have called the Space Robotics Lab here at ITRL. And so this laboratory is within the scope of a larger project, which is a Discover project. And the main idea of this project, which is a WASP-funded NEST, is to look at space systems and underwater systems from the same holistic point of view, from a control and planning perspective. So what's the goal here? We want to look at what's common between these and find and tackle those common challenges. So if we look at this kind of table and we look at space systems and control, we see that we have a lot of energy constraints. We sometimes need to deal with harsh dynamics like slosh dynamics. And we also have inaccurate actuation when we actuate our system. So these are things that the control system should be able to handle and be robust to. From a planning point of view, we also have large scale planning because we sometimes deal with long orbits, even if you are doing just around the Earth or maybe around the solar system. And we also have a lot of computational burden because these systems tend to be quite simple computationally wise. And then, of course, we also need to deal sometimes in the future with interaction with structures for inspection, for detumbling. And in these cases, the safety of these interactions is, of course, primordial for our task. If we look at the underwater scenario, we will have a different type of challenges, but some are still very similar. So one of them is we only have sporadic communication underwater because underwater communication is very harsh and very low bandwidth. We also have ocean currents, which our system needs to reject in order to do a successful task. And we still want to have a robust control system because even if we interact with structures and we are in the presence of these ocean currents, we shouldn't damage anything around us, inclusive humans. On a planning context, we also have plannings with external forces. These, of course, look like ocean currents, but also at the local level, turbulence around structures. And we also have to keep into account that this planning, if we are cooperating with multi-agent systems, needs to take into account that the communication will be intermittent. So how can we have a planner that can leverage these? So based on these challenges, we essentially divided the common challenges of this work or of this project. And we look on the control side to non-trivial dynamics, energy constraints, robustness of the control system, which are techniques or that are properties desired across both environments. And on a planning side, we're looking to non-trivial dynamics, long look-aheads, and safety. And these are, of course, also desirable both on space and underwater systems. So how are we going to tackle these? So we essentially started by creating, let's say, 3 main research pillars. So the first one is control in weightless environments. And here we are looking into robust control in these varying dynamic conditions. So what does this mean? This means that we are trying to do control both dealing with underwater currents, turbulence, but also with uncertainty in the actuation of our system, which of course can be the thrusters underwater, but also our thrusters in space. With provably safe recovery of communication and actuation. So this means that when we lose communication with another agent or one of our actuators broke, we should still be able to have some guarantee of the safety of that system, at least until a given threshold in the actuation and communication. Then we also want to explore multi-agent settings with robust formation control and load transportation. So these are tasks that tend to be very desirable both in space, but also starting to appear in the underwater scenarios. In particular, in space, we start to observe that of the interest of not only having larger and more efficient formations of satellites, so like the Starlink is one of those cases, but also transporting loads for the orbiting defunct space systems, for instance. Underwater, we can also use these formations to have a larger cover of an environmental monitoring task, and we can also use the load transportation to start assemble and move debris from one place to another and start to clean also our ocean. So these have been tasks that have been looked at as well. And we also are trying to look into the increased autonomy of scalable swarm control. And so what does this mean is that we are now not leading just with formations of 3 to 5 to 10 agents, but maybe thousands and millions of spacecrafts. And how can we do this in an efficient way? How can we do this in a way that the system will behave correctly and will not be a huge burden for everyone? The second research pillar is dealing with planning in weightless environments. And here we are looking essentially on how we can combine temporal aspects of the planning with safety aspects of the same planning. And so what we want to do here, for instance, is if you look at the image, you have some goal that we need to take our system to, and there are some region that we need to avoid. So here the places where we need to be are marked in green, and there is an associated timestamp with it. And then an area in which we don't want to be is marked in dark red, and that's also with a given time instance. And so what we want to do in this task is we can use this type of logic. So in this case, F means eventually, and G stands for always. And so what we want is like from 0 to 15B, leave our starting point, and then we want to be always out of the region that is marked in dark red. So that is like an obstacle, for instance, that we want to avoid. And eventually we want to be between time 6 and 8 seconds, for instance, in the first green region, between time 11 and 15 seconds on the second, and between 11 and 15 on the last one. So these are plannings that we're looking into. We are called them signal temporal logics. And what we want to do is essentially transport these and combine them with a proper controller so that we can have more robust systems. So what's the advantage of this type of planning is that they are by design verifiable and safe. So that means that by design, we can construct a safe planner that we can deploy in these systems. And there are still challenges associated with them, particularly on what it comes on shared workspace and multi-agent settings. And then lastly, we also want to look into the increased autonomy of modular systems. And what we want to do in this point is essentially to combine multiple robotic agents in a way that enhance their capabilities. So one example that we are looking into is how we can combine 2 underwater robots. And these are not holonomic. And what does holonomic mean? It essentially means that we can move in any direction with any attitude. But if we can combine multiple of them, then we can essentially add up the missing degrees of freedom and create an autonomous holonomic unit that is composed by multiple subcomponents. So these are some of the tasks that we are trying to develop here. And then lastly, the third research pillar, which is where the Space Robotics Lab also comes in, deals with the validation in space systems. And this is the structure that we are trying to set up here with the support of ITRL, and also with the validation on subsea, in which we are working with SMARC to achieve this. So then the last piece of the puzzle is that we want to do a cross-compatibility assessment. So I started by saying that we want to look into these scenarios from an holistic point of view, but this doesn't mean much if we can show that the same controller and planner can work on these two platforms, and we can transport the properties of these and adjust them given that we have different disturbances or different actuation properties. But in essence, if we can design these controllers taking this into account, then it's just changing, let's say, some numbers, and we have maybe a different radius of safety that we can stay in, or a slightly different planner to account for different properties of the environment. And that's what we want to do lastly on this point. So how does this look like for now? So at this point, we are starting to build an air carriage. We are working hard to set up an even floor where we can do microgravity experiments. And if things go well in the future, what we would like to have is something that looks like this, which is the Aerospace Controls Lab or at Caltech. And so there they have a very similar structure to what we want to do with also multi-agent systems. And we are trying to use this like as an inspiration, let's say, and try to do different work, of course, than what has been done. So how do the experiments work? And maybe I'll here end up more or less in the same fashion as Kai. I'll show two videos and I'll try to remove the sound in them so I can speak. Let's see if this works out fine. I think I cannot remove the sound. Okay. Yeah, because I cannot have. Okay, maybe you have can. Okay. Here it works. So what we have here is essentially an experiment that we did, and this is kind of to show, okay, like what's the end result of this. So here it's an experiment that we have done using the NASA Astra B robots, and what we want to show here is that we are dealing in an environment which is in this case, two autonomous systems trying to do a formation control task and trying to distribute themselves along the environment. And we are dealing with localization systems that are not accurate, so we don't really have a motion capture system inside. The way these work is by essentially having a map that was built previously and then trying to localize with respect to said map. But when we are inside these structures, well, lightning conditions change a lot. We have cables in a lot of areas, and these also interfere with our ability to detect where previously these cables were and where they are now, and also give us some localization. So these are some challenges that we are trying to also overtake by using vision-based methods and other robust methods. And then on the right, there's a small example of SAM, which is like a small AUV that is built by Smart. And the goal here is to show you what these experiments look like. So here is an experiment in the archipelago of Stockholm, next to Douro. And this is a simple navigation task. But what we want to do later is to combine multiple of these. So here in this case, you can also see a tether that is used to keep communication with the vehicle. And if something goes wrong, you can also push the tether and the robot comes with it. So yeah, that's essentially it from my side. I don't know if you have any questions.
Are there any questions from the audience to start with? No? Then I will start. And I wanted to ask you if you can share some details about the robot platform that you have built here.
So essentially the robotic platform that we are building, and maybe it's easier if I go to that. So this platform we are building essentially from scratch, but what this kind of resembles is we have some compressed air cylinders inside, some compressed air tanks. And then we have what we call air bearings. So these air bearings essentially receive pressurized air, and they create a very, very small air cushion between the vehicle and the surface. So what does this do? This means that now we have a total separation from that surface, and we no longer have any friction with the floor below us. So this resembles what we kind of have in space, of course, minus the air drag that we have in the environment. And if we push this robot, then it will just be drifting. Or if the floor is not even, then you have like essentially drift motion. So this essentially is like the basis for our test. And then on top of that, you can add whatever control or whatever computer system you want. Sensors, we are trying to equip these with actuation systems that are similar to what we find in space. So thrusters that we can control in a discrete way, like a solenoid valve, and also adding some intelligence to it with onboard computers and trying to essentially come up with algorithms that can work on these environments, but also that we can transport and essentially test at the NASA Astra V platform, which is for now what we are trying to do. So the software that we'll be using on this, it's essentially the same software that runs on the NASA Astra Vs, and we have been working with the NASA team to port the code to ROS2 so that we can have like a long-lasting platform. And this has been, I think, a very fruitful work that we have done together. So yeah, ROS2, everyone that works in robotics, and almost everyone uses ROS, and the actuation is also very similar to what you would face on the environment. Yeah.
Nice. And do you have planned to test with the Astra V as well? Or have you done that already?
Yeah, so I have done that in the past. We have an idea of doing some tests with that. We probably will start to have those maybe towards the end of the project if things go well. This is something we still have to set up. We're also trying to do something similar at the European level. So we're trying to explore that. I mean, we are in Europe, so there should be something we could do here. But for now, the platforms that we have available at the space station is the NASA Astra V. So that for now is kind of the problem.
Yeah, thank you so much. Looking forward to that. Oh.
Yeah, so you mentioned the two different platforms or domains where and you want to find where sort of your solutions carry over, where you can use sort of similar approaches for both environments. How do you, or how does this carry over to ground robotics and ground transportation?
Right, that's a great question. So if you look at the underwater system that we had, so this SAM UAV, it's essentially like a non-holonomic system. So you can look at it as like a truck, but in 3D. So if these algorithms work well on a non-holonomic system, then transporting this maybe to actually a real truck, of course, can be done, but there are some caveats. So the actuation system is inherently different. Maybe the planner is also. We can try to come up with ideas on how to also merge these two and have them converge somewhere where we have like a balance between like how detailed our scheme is and how tunable it is to both environments. So I think there's like a trade-off that we have to do there. But I think it would be super interesting to also test the same control and planning methods of SAM on maybe like the smaller truck that we had here at SML at first. And then maybe things go well, maybe go to the bigger RCV. That would be interesting to see.
Thank you so much for your presentation. And I will invite Mikael to join us here.
Yes. Okay, so good morning, everyone. My name is Mikael Nybacka, Associate Professor in Vehicle Dynamics. I'm also responsible for the research concept vehicles at ITRL. So if any one of you have an interest of engaging in the RCVs with regards to research or education, you can come to me and we can plan how that could be done. So let us introduce it. First then, so to reach our sustainable transport system, we need to solve a very complicated puzzle. And one way to understand and solve this puzzle is to test and evaluate possible solutions in both real life and with real users and in real systems. And this, of course, then requires either platforms or we do this out in real life, in living scenarios, in living labs. And there we can integrate our research together with our partners. And that is an important part of the research that we do here at ITRL and why we have these kind of platforms. So looking back at the history, so we started already in 2012 developing the first RCV, which we call just RCV, stands for Research Concept Vehicles, of course. That is being decommissioned because we are re-engineering that together with our students and faculty to become something looking like this, hopefully a bit more bodywork as well on it. And this vehicle, the initial one, had a large degree of actuators, so we can control the wheel torques individually on each wheel. We control the steering angle individually on each wheel, and we can control the camber angle, the tilting angle of the wheels individually. For the new vehicle, we will also add active suspension, so we can also control the ride height of each of the wheel individually, up to hopefully 2 hertz at least. What we also have in the new vehicle is more powerful battery as well as in-wheel motors, meaning that we will be able to do more dynamic driving tasks, hence the name RCV Dynamics. So we will be able to control the torque all the way to full slip, so we can do evasive maneuver studies, more harsh fault tolerant control studies, and so on. So that is what we are aiming with this vehicle. And much higher speeds as well. This has a top speed of 70 kilometers an hour. This one will have a software limited top speed for safety. Much higher we can go. Okay. Then we also have these bigger ones that resembles this new pod-like systems that we see coming up with regards to autonomous vehicles. So a similar size to these autonomous pods that are being driven here and there. And these platforms are less over-actuated, but we can still control the torques individually on each wheel, the steering angle individually on each of the wheels. And they are also designed so that it's relatively easy to mount systems on the platform. If it is a new sensors or some battery system or something else. A complete new driving system as well, which you will see on the next slide. So the black here is to be continued developed in a connected and automated area, whereas the blue one here is open for larger rebuild, if anyone are interested in that. We had a discussion before with some faculty of going more electric systems on it, with induction charging and so on. That is an area where we can go, but we can also do other development of that platform. So let me know if you have ideas. Okay, yes, some small examples of the kind of research that we have done and what you can do. If we look at to the left there, we have done research on fault tolerant control. So given if we have a fault happening to the vehicle that results in motion change of the vehicle, so the vehicle will behave differently. In this case, we have a braking force on one of the wheels due to brake failure, inverter shutdown in electric machine, etc. That will create the yaw motion, making the vehicle basically steer over to the other lane, which can be a frontal accident, which is bad. So then what we can study with these platforms is that we can infuse these faults into the platform digitally or mechanically. And then we can study the control, how we can utilize the rest of the actuators to mitigate this fault. The middle picture is an example of where we have done collaboration with University of Malaga in Spain, where they do research on self-learning ABS system using spiking neural networks. So one of the issues with ABS system is that we don't really know all the time what the friction is, what is the vehicle driving on. So then one way to mitigate this is to have a self-learning ABS system that is able to learn and tune the controller online so that it can handle this situation. So here we have then developed this electrohydraulic brake system. So we have a brake blending, blending both the brake torque from the motor and this electrohydraulic brake system individually on each wheel. Then the last one, which we'll hear a little bit more with the next speaker after me, Shushin. But here we have done studies on driver-operator vehicle interaction, where we have studied teleoperated driving, where we have equipped the vehicle with cameras and additional driving station. So here you can see that we have the same driving station in the vehicle as we also do on the remote side in teleoperation. And this gives us a good basis when doing driver or human vehicle interaction studies, so that we have the same interface in both places. So that shows a little bit on how modularity we can move this around. Okay, so then I would like to show you some videos. So here we have one video showing more human-vehicle interaction, where we look at the mental workload of doing various driving tasks with the brain-computer interface, as well as heart rate variability, in order to see how we can create a good metric in understanding better the mental workload of a driver or an operator. It's there. This is a picture of being time where you see more of the directly.
Det är som att köra en fyrhjulig motorcykel ungefär.
Okay, thank you.
For the presentation, are there any questions from the audience here? You're running a bit tight on time, so if there are any questions, sorry, I would like to prioritize those.
Yes.
First. Well, I was curious to know, I mean, you discussed a little bit the Untitled Chapter, the RCV dynamics, but how about the new development for the RCVs? Do you have anything new coming up for that?
We had discussion as well to continue working on the perception side of it. And there we are looking for people who can engage in the platform and doing more of the perception, planning, localization, and all of that, so that we get that functionality as well to a good base level, which would be good for many other experiments as well. And hopefully we can again try to get the permit to drive these on campus. We have tried before, but since it's an own built vehicle, we are struggling a little bit on the permit side. But we will try that again, and hopefully we can get that to be accepted for driving on campus at least, which will help as well.
That would be very interesting. I have another question. I mean, if there are any students listening, can you describe how you usually, which kind of projects do you usually have if someone is interested in working on the RCV?
Good point, and it varies a little bit. We have had project courses from mechatronics HK course, the machine design similar project course in automatic control, as well as the project course in vehicle dynamics. So their students are coming from many different programs, and sometimes we have managed to put several programs together in terms of the project courses on the platform, which have been a good experience for the students, I believe.
Thank you so much.
Yes, thank you.
Question? No. Okay, then I invite Sujin here to talk about the remote driving simulator.
Okay. Hi, everyone, and thank you, Elisa, for having me here and working so hard to pronounce my name. Okay. Hi, I'm Xujing Song, and I'm the research engineer now at the Vehicle Dynamics. And I will talk about the remote driving station, our remote driving station. But I'm gonna start with the automated vehicles. If we think about the automated vehicles, it's really developing very rapidly this years. but there are still many remaining questions before they fully achieve level 5 automated vehicles. For example, as some complicated situations like road constructions and some public events happening on the roads, it is kind of hard for the automated vehicles to deal with them. So in those kind of situations, the remote driving could be a good backup system for the human operators to overtake or supervise the car by like directly controlling them, controlling the car or select the road for them. And also remote driving is now, maybe someone the remote driving is already applicated in some industries like the mining industry. So the workers can control the mining trucks from above the ground. Not only improve the efficiency, but also what's more importantly, that it minimize the risk for the workers. And so we build this remote driving station to study the teleoperation. And since the remote driving is largely different experiences from the real driving experience. So the first research question is that how the real life driving different from the remote driving. And then we also want to figure out how does different feedback affects the driver. For example, how does driver react to different feedback combinations? So this is why we have this remote driving station and this remote driving platform that Mikhail mentioned about before. So the teleoperated vehicle is our RCVE equipped with some sensors, and the information that the sensors get are transmitted to our remote driving station on the right side. The remote driver on our driving station can make some decisions according to those informations, and those decisions, which are driving commands, are transmitted back to our RCVE, so the RCVE can operate according to their commands. And so, besides connection with the RCVE, our remote driving station can also connect with the SWIA car in the first part that Kaj talked about in the Smart Mobility Lab. Which means our remote driving station is highly integrated with the whole ITRL lab. Yes, and if we zoom in on the right part of the remote driving station, only looking at it, it is very important that how the remote operator can feel the surroundings of the real car. So we implemented by having several feedback systems to the remote driver. The first one is the visual feedback. Here we have one big screen, but we can also have 4 or 6 monitors combinations to see the 360 degrees around the car. And the second one is the sound feedback. We use 5.1 speakers setup to provide the spatial sound to the remote driver. So if one car is approaching, if another car is approaching, the remote driver can know where the car is located, not only from the video, but also from the sound, where the sound is come from. And the next one is the motion feedback, which is provided by the moving platform under the driving chair, which is 6-degree freedom, make it obvious for the remote driver when the car passing a speed bump or passing cobblestone road. And then the first one is the steering feedback. Our Fanatec steering motor can provide very powerful steering feedback force when the remote driver is operating. So the driver can make more precisely steering when they're driving. The finally we have the vibration feedback, which is provided by the vibration actuator, and this mimic the engine vibration on the car. So all those subsystems together give a realistic driving experience to the remote driver. Yes, and we have done several studies on this remote driving station, but I will talk. This picture is from a newly finished experiment, actually finished just at the beginning of May. And we recruited 35 participants in this experiment, and this lasts for 2 months in total. This study is about how does different traffic interactions affect the driver's behavior and their fatigue level in the remote driving task. So each participant drive in 3 simulated scenarios, including the highway, country road, and the city network. We build a big city in the simulation. And when they are driving, we also collect some physiological data from the driver to see their status during the whole process. They include the EEG, also known as a brainwave signal, and the ECG, also known as the heart rate signal. So we can analyze their nervous level, their mental workload level, their concentration level, things like that. And we also have video recording for the participants, so we can analyze their facial expressions and their body gesture during when they're driving, so to see the changes of their driving behavior. And the last one is we also collect some subjective data, like the questionnaires they fill in before and after each test. Yes, because this study is actually finished very lately, so I don't have any drawing conclusion for you, but what I can say is we see a significant difference, like fatigue level and different driving behavior patterns in different task groups. And you can expect more results from us later. Okay, so I will show you one video for this test. Yes. Okay, so the driver is driving. So now it's the city road scenario, and you can see the driver is passing a speed bump, and the chair is moving as the same as the video. And there is another car passing by and ahead of the driver. There are some other traffic lights or traffic signs on the road also, which is we want to simulate the same as you're driving in the city. And now it's a highway scenario that the driver is overtaking from the left. Of course, he's overspeeding too much comparing to you driving. And we engage the motion platform in this time. Okay. So in this experiment, we only use the software simulation for the driver to drive. But in previous study, we also used some real remote driving, which is this last video that I will show you. Sorry for being too loud. But this study is mainly about different steering feedback force model. How does they impact the driving behavior in the remote driving? Okay, I think that's everything from me. I'll take questions if you have any.
Are there any questions here or online? No? Okay, then I will start. Yeah, I was wondering, I was wondering, how do you deal with latency in the system? If you have experienced any problem with that, if you have any plans for the future?
Yes, I think that's a very good question. That latency is a very important part in the teleoperation. And there are actually the latency comes from two parts. The main part is the transmission, the communication between the real car and the driving station. But the driving station itself have some sort of latency itself. But about the main latency, it's actually our next step in the future, maybe after autumn. So we are upgrading our the connection of RCVE and our driving simulation, the driving station itself. And after we upgraded it, we're gonna try to reduce the latency during the teleoperation. So we will use some algorithm to predict the latency and then reduce the latency.
Thank you. Okay, but then last 5 minutes, I would like to invite all the speakers back for a final discussion. Again, if anyone online wants to ask any questions, please raise your hand or write in the chat. Also here, of course. But otherwise, I was wondering if you can tell us something, because a lot of the people might come back at the end of August for the real or in-person lab tour. I was wondering if you could share some small insights of what you're looking forward in terms of development of the platforms in the upcoming month and what they might see when they come here.
Thank you. Okay. So if things go according to the plan, and that's always a big if in research, I think by the end of August or like maybe mid of August, we already have one platform operational, and maybe we'll have a prepared demo for that time. But this depends on a few ifs. So that's essentially the plan. We are working towards that and to have these platforms available as soon as possible.
So referring back to the last open house, we did a demo on how vehicles and the infrastructure interacts. And for the next open house, we were planning to extend that and investigate even further in how can the infrastructure support the vehicles, and probably also guide the vehicles and set local guidelines in maybe speed limits or saying giving heads up around the corners or in different traffic scenarios.
Yes. And at the demo day, hopefully we can get upgraded of the teleoperation down so people can test drive the remote driving themselves. That's super exciting.
Yes, and in the project REDA 2, hopefully with collaboration with one of the partners in that project, ICTech, we can also implement the spatial audio on the RCVE so that people can hear the difference it makes as a remote operator having spatial audio.
Is that sound from the environment, other vehicles and so on, or is it the sound that emanates from the own vehicle?
Both. It can be both, and it can also be augmented. So.
Okay, great. I want to thank you all so much for joining today and for presenting your work so well. And yes, I mean, we hope to see as many people as possible at the open hours after summer. And yeah, we'll continue the discussion now with and coffee here. And yeah, thank you so much.
Thank you.